Hello. This time we're going to go over the notion of injectivity of a function, and well, we're trying to come up with a numerical motivation for the introduction of this concept. Numerical in the sense of comparing just collections of things. So start with a function where from A to B, right? Just indicated here, where A is the domain, B is the codomain, meaning that for every single input there is a unique output, right, in B. Now, it doesn't say that every single thing in B is the output of something, right? But it says that every single thing in A is an input. Okay, so what is the condition that we're going to consider now? Well, where every two different elements of A are paired with different elements of B. Now, to put this in a more formal language, right, just a little bit more, just a little bit, we would say that for each x and y in A, if x is different from y, then f of x is different from f of y. Now, makes perfect sense in the way that we just define it, but you may also define this thing using an equivalent version, using the contrapositive of this conditional statement. You may also say that if f of x is equal to f of y, then x is equal to y. So, meaning that if you see two outputs that are identical, that means that they come from the same input. But let's exemplify this with just some graphics. Once again, it's not a problem. Have something along these lines. Let's say that I have 1, 2, 3. Those are my elements here on this side, and I have these other elements A, B, C, D. I'll say that I associate 1 with A, 2 with C, and 3 with D. Okay, clearly every two different elements from this collection that I'm signaling here are associated with two different elements from the other side, right? From the codomain. Now, that means that this function that we're defining here in this diagram satisfies the condition that we just indicated here. Now, what about the other, right? How is it we can detect that this is not actually the case? Well, let me exemplify it one more time. Right? I'll provide another function. Right? Again, it may have different formats. It might be as a rule, as a table, or as a diagram. It really, the representation is relevant depending on the context. So let's say that we have 1, 2, 3, and 4. Right, on this side, and I have A, B, and C on this other. Well, for that one, say we make this association. 2 goes to B, 3 goes to B, and 4 goes to C. Well, here, what we see is that we are making an association. 2 goes to B, something to signal. 3 goes to B as well. So here we have two different inputs, namely 2 and 3, going to the same value on the codomain, namely B. Well, clearly, right, we have two different elements that do not result in different outputs, right? So that function doesn't satisfy the condition that we're indicating here. Now, but if we look at these examples here and we see the number of things that they have, well, we can see that in this case where the condition is satisfied, the number of things on the left is less than or equal than the number of things on the right. But how is that we can observe this, let's say, as a process? Well, imagine for a moment that you were to remove the elements from the domain one by one. right? Well, every time that you remove something on the domain, you will also have to remove something from the codomain. But what we see is that it only is going to be removed only once. So effectively, when you remove something on A, the domain, you will remove one thing on the other side, B, the codomain. Okay? So what does that mean in terms of numbers? Right? Well, the following. We see that under this condition, the number of things in A is less than or equal than the number of things in B. Well, this intuition that we use to compare collections motivates the following definition. Is nothing else but an urgency to count, to compare collections. Let f from A to B be a function. F is injective. Well, if for every pair x and y in A, we have that x different from y implies f of x different from f of y. Equivalently, right, you may also write f of x equal to f of y equal implies that x is equal to y. Now, something to notice is that the converse of this conditional statement is nothing else but the determinism of a function, right? Meaning, when you input something, it produces only one output. And, well, that's it. Hope that you enjoy it. See you next time.